Let us start lecture 54, and the course is on phase diagrams in single component and binary systems. And the topic of this lecture is on delta G mix, which is Gibbs free energy of mixing, and phase diagram when the system deviates from ideality. So, till now what we are doing, we are trying to understand how the shape of delta G mix would appear under different conditions of del H mix. And we have taken 4 conditions. What are those 4 conditions? One is delta H mix is 0, which is ideal case. Delta H mix is slightly negative. So, this is non-ideal. Delta H mix is slightly positive, and delta H mix is large positive. And in all 4 cases, we have seen how the plot changes, that is delta G mix versus composition plot. Now, we will gradually switch from all those understanding, whatever we have learnt, those learning will be using to draw phase diagrams when the situation is or when the system goes away from or the moves away from ideality. And remember, here we have taken a regular solution approach, and in order to address a non-ideal situation. So, let us see what we have. Just brief, we are taking regular solution model in order to form binary solution with A and B and at a particular temperature and pressure. Pressure is kept at 1 atmosphere, and this one is X A and X B are the mole fraction, and we are getting 1 mole of solution. Fine. And we have actually taken 3 conditions, the 4 conditions. Case 1, which is omega equal to 0, delta H mix equal to 0. Case 2, omega is less than 0 and delta H mix is less than 0. Case 3, omega is slightly positive and delta H mix is slightly positive, and case 4, omega is large positive and delta H mix is large positive. All those 4 cases we have considered, and remember, every time we are actually doing it using the formula, which is delta G mix equal to delta H mix minus T del S mix. So, this del S mix, whether we are considering ideal or non-ideal, all cases that will be only considering configurational entropy term. Other entropy term will be ignored. So, now here del S mix is same in both cases, minus R X A ln X A plus X B ln X B, and delta H mix equal to omega X A X B. So, now it is very clear that if omega is 0, delta H mix is 0, which turns out to be ideal solution. So, this is basically ideal solution, and all 3 cases these are non-ideal. Fine. And if I write it fully, omega X A X B plus R T X A ln X A plus X B ln X B. We have also seen that this can be related to another parameter, which is alpha X A X B. We have found alpha critical, where the delta G mix plot with composition just started appearing, just started getting the inflection. Okay. So, that can be related to omega r t. In fact, from this we can actually get T critical. So, the T critical is nothing but omega r alpha, and since alpha is 2. So, alpha critical we have found as 2. So, we can write it as 2 r. So, we can see that T critical can also be found out with omega by 2 r. When I talked about these first 3 cases, the first 3 cases, the shape of free energy line is like this. So, this is 0, 0, 0, x b equal to 1, x b equal to 0, and this is delta G mix, and x b is changing this way. So, I have seen that if it is, this is case, let us say 3, then case 2 would be, this is case 2, this one should be case 1 and this one would be case 2. Okay. We have seen that before, but when I talked about case 4, so this is case 1, 2, 3. But if I talked about when we discussed case 4, so case 4 was like this, fine. This is delta G mix x b equal to 1, x b equal to 0, and x b is varying this way. This is 0, 0 value for delta G mix. So, this is case 4, fine. Now, if I look at, in fact, in this particular case, in one of the lectures, earlier lectures, we have also considered the effect of temperature. So, as we increase the temperature, if we see that all those plots will further go down, it will be much steeper downward, and that will remain convex downward. So, for example, I increase the temperature, this is at a particular temperature T. So, if I increase the temperature, that plot, let us say third case, the plot would be, like this. Let us say whether I take case 2, at T equal to T 1 and T 1 is greater than T. Okay. So, why? Because delta H mix is independent of temperature. We have seen that before. So, delta H mix, this is also we can write delta H mix is independent of temperature. But if we increase temperature, so then the main influence would be on the minus T del S mix. So, it will further go down, much steeper convex downward and steep, much steep downward. Okay. So, this particular one will actually take the drag, this particular one will drag delta G mix versus x b plot steeper convex downward, fine. So, that is what we have learnt also. Now, if I try to look at the case 4, what would happen? The case 4 will see that let us say effect of temperature increase on case 4. So, this is the 0 0 line, and composition is changing this way, x p equal to 1, x p equal to 0, delta G mix. So, let us say at a very high value of delta H mix, let us say delta G mix plot is like this. We know why there is a dip here. Okay. So, now this is at a particular temperature, let us say T 1. Now, if I increase the temperature, so then I can have a situation like this, delta H mix, which would not vary with temperature. This is delta G mix if I try to plot. So, delta G mix is nothing but this delta H mix minus T del S mix, fine. So, this term will further go down. So, if I draw two cases, one is with this is minus T del S mix or T 1 let us say, and if I increase the temperature, delta H mix position will not change, but this position will change. So, this position would be, let us say this. So, this is T 2 del S mix minus. So, now the first case, my delta G mix plot would be like this, and the second case the delta G mix plot would be like this. So, this is delta G mix at T equal to T 1, and this one is delta G mix at T equal to T 2, and T 2 is greater than T 1. So, if I try to look at equilibrium phases between the two minima points of delta G mix plot, so one equilibrium will be set up here. This is the common tangent. The another common tangent I can have for T 2, this one. So, the composition which will be stable between two minima will be those two. So, this is one composition and this is one composition, and the T which is at T 1, and the T 2 would be these two. Okay. So, as I see that as we increase the temperature, the two composition minima will actually shift towards each other, okay, rather than moving away from it. But if I decrease the temperature, they will move away from each other. Okay. So, now if I increase the temperature, the change in the plot pattern would be like this. So, this is at T 1, then let us say this is at T 2, then this is at T 3, this is schematically drawn, remember. Then we have this is at T 4, let us say, and then finally, we will arrive at a situation which will be just like critical alpha, we will reach a critical T critical, and then finally, we will get del G plot would be all throughout the composition convex downward. Okay. So, this is at T 1, this is at T 2, this is at T 3, this is at T4, this is at T5, and the final one is T6, and we have a relation between those temperatures. T1 is less than T2, less than T3, less than T4, less than T5 and less than T6. So, if I see the common tangent are basically passing through those two minima. This is one, second one is this, third one is this, fourth one is this, fifth one is just one single point, and it is basically T critical, and the final one we have no inflection. This is actually, this is belonging to a critical temperature, fine. So, we see that as the composition, and let me see that this particular thing is drawn at a temperature which is less than all those temperature starting from T1 to T6. Let us say they are below TMA, below TMB. So, if I try to look at free energy versus temperature, so this is GB naught and this is for solid, this is GB naught for liquid, hence this particular temperature is TMB, and we can have a plot for metal A, solid, this is G naught A for liquid. So, this temperature is Tm A, melting point of A, and all, let us say C, all the temperature so this is let us say T1, this is T6. So, this T1 to T6 are lying here. So, in that situation I can actually take the pure B solid to be my reference standard state, which is solid, which can be taken as 0, and here also I can take G A naught solid, which can be taken as 0, because from T1 to T6 for A, solid is the most stable and solid B is the most stable, as well as solid A would be the most stable for both the metals. And that case, these lines will be same as G2 solid, because G1 would be, since G1 equal to X A G A naught plus X B G B naught. Here we are considering solid. So, this should be 0. So, then G2 solution is nothing but G1 plus delta G mix. So, this G1 goes to 0. So, hence this is equal to delta G mix. So, the delta G mix plot is nothing but the solid solution free energy. So, in that case, all those common tangent passing through that 2 points minima point, those will be the stable phases in that system, and that composition of those two phases, as we increase temperature, they are coming closer to each other. Okay. So, in fact, that same information we can actually plot over temperature composition plot. Okay. So, let me see how to reflect that. So, I see that, let me draw it here. Let us say this is x b varying this way, x b equal to 1, x b equal to 0. I have taken let us say this is T m A and this part is T m B, and TMA and TMB is more than TMA, and I am taking temperature, first temperature let us say is T6, which is the highest temperature below TMA. So, T6 all are solid, because solid free energy is convex downward all throughout. This is T6. Now, at T5, I am seeing that that is a critical point appearing. Okay. So, that tangent is actually that critical point, if we do the second derivative we should get that critical point, that is the point, and let us say T4, let us say this is T4. The T4 case, these two compositions are lying at these two locations. Now, T3, these are located here. T2, I am just taking those compositions at the same temperature, because every time I am doing one curve is at a particular same temperature, delta H mix is not changing. So, T2 we have the composition here, and at T1 I see composition here. So, if I connect those, I am getting a dome. Okay. In fact, in the phase diagram we do see such domes, and that dome appears when a situation in the situation where delta H mix is highly positive. It suggests, and also remember our first assumption, one of the assumptions when considering regular solution model was both the pure metals are having same crystal structure, even the solution that is forming, that is also having the same crystal structure. So, the crystal structure wise this particular two minima points over this common tangent, crystal structure wise they are same, but if I try to look at their compositions are distinct. Both the composition to the extreme ends are basically having A rich side or B rich side. So, that means they can be considered as two different phases. As we understand, the phase definition is a compositionally homogeneous, physically distinct part of a system, and so here we see that only those minima point across that tangent will have unique composition. All the other composition between those two minima point will segregate into these two conditions. So, we say that this is phase separation. So, in fact, when we have such situation, the phase separation, as we go lower and lower temperature, they will extend its gap between these two compositions. So, they would become more preferably phase separated. Okay. As we go higher and higher temperature, the phase separation will go off slowly, and at one particular temperature, critical temperature, the phase separation will go off, and everything would be a single phase solid solution. Here we are taking solid solutions. Okay. So, this kind of situation when it appears, it is called a phase separated phase diagram. So, phase diagram phase separation, and remember pressure we are taking as 1 atmosphere. So, we can see that this is beyond this particular temperature, beyond this particular T5 temperature, everything would be a single phase solid solution till we reach to TMA. Okay. So, now as we see that whenever we have delta G mix to have such shape, convex downward as well as convex upward, we do get phase separation, and the plot of phase separation is like this. And since they have same crystal structures as we have observed, so we can actually write this solution as S1 plus S2, and S1 and S2 are two phase separated solutions, fine. And here I am writing because both have same crystal structure. But this phase separation actually indicates that similar type of atoms they would like to have around its neighbor. Okay. So, it means similar types of atoms like AA and BB would like to have their existence. Fine. So, this is nothing but the phase separation. So, we will end today this particular discussion. So, next class onwards we will also look at one important aspect of diffusion. So, there are two types of diffusion we can explain using the typical plot of Gibbs free energy of mixing with composition. One is downhill diffusion, another one is uphill diffusion. So, downhill diffusion and both can happen. The downhill diffusion is actually due to the diffusion of a particular species from higher concentration to lower concentration. But uphill diffusion is about when the migration of a particular component happens from lower concentration to higher concentration, okay, against the composition gradient. But at the same time we will see that if I take activity wise the component movement would always be higher to lower activity, but when I take mole fraction the situation changes. So, that part we will explain in our next discussion, and also we will take up combinations of different enthalpy of mixing. Now, we will take two solutions, one is solid solution and liquid solution having different values of omega or delta H mix like 0, greater than or less than 0 for both the cases, and see while we do that combinations what kind of phase diagrams would arrive at. Okay. So, that part we will take up in our future discussions. Let me stop here. Thank you very much.